Hello everybody. I've decided to finish up the notes that we didn't finish in class today. So the day 107 notes. I know in period 4 we got just slightly a little more ahead than where we got in period 7. So please bear with me, period 4 students, that this is the first part of this video is going to be a little bit of a recap of what we finished up with. In period 7, we left off with, we figured out what u was equal to, we figured out what dx was equal to, so now we were going to make the necessary substitutions. So you'll see that u is equal to x squared plus 1. So if you notice here, instead of x squared plus 1 in the denominator, now we have a u. And now we also saw that dx was equal to du over 2x. So instead of a dx in the denominator, we now have a du over 2x. Okay? X still stays the same, but otherwise those are the two main substitutions that we made. So at this point, hopefully at this point, you can see that there is some cancellation. The x in the numerator cancels out with the x in the denominator. So you're left with now, as your new expression, the integral of 1 over u times du over 2. Okay, so the x's cancel out. And at this point, since we have division by 2, we can rewrite this as just multiplication by 1/2. So we have 1/2 times 1 over u du. And at the beginning of this lesson, hopefully, you recall that when we take the antiderivative of 1 over u, that's where we get the natural log. So now we get 1/2 natural log. Don't forget the absolute value of u. Now we just we make the substitution of u back in. So we get 1/2 natural log absolute value x squared plus 1. And our interval is still 0 to 3. Now recall that the way we evaluate the interval is that we plug in both 0 and 3, and then we subtract. So we plug in, so let me put this, I'll use black here. Let me put this over here. So we have 1/2 natural log of the absolute value. If we plug in 3, we get 3 squared. 3 squared plus 1 is 10, so the absolute value, or just 10, since the absolute value of 10 is just 10 at this point, minus 1/2 natural log. If we plug in 0, we get 0 squared. 0 squared plus 1 is 1, so the natural log of 1. Excuse me. Sorry about that. Now at this point, without a calculator, there isn't much we can do. We actually do know that the natural log of 1 is 0, so this just becomes 0. So at this point, without a calculator, our answer will just be 1/2 natural log of 10. So that is the area of the region bounded by the graph, the x-axis, and the line x equals 3. All right, so now let's move on. So now let's look at A and B. Now A and B, hopefully, there should be some giveaways here that our equation is going to end up being, our answer or antiderivative ends up being natural log. And the giveaway hopefully should be, if you look at the denominator of both these functions, you'll notice that the derivative of the denominator is 3x squared plus 1 in the first problem, and in the second problem, it is secant squared plus x. Now, why is that relevant to both of these? Well, hopefully you should notice that the derivative is the numerator for both of these equations. So the derivative of x cubed plus x is 3x squared plus 1. That's the numerator of that equation. The derivative of tangent is secant squared of x, and that happens to be the numerator of that of that second equation. So at this point, whether some of you can make this jump is one thing, but hopefully at this point some of you can say, all right, well, I know the derivative of 1 over something is the natural log. So natural log of the absolute value of x cubed plus x, and that is our answer. And then the second one, natural log absolute value of tangent of x plus c. And once again, we can easily check our answers. If we were to take the derivative of both these answers, let's say if we take the derivative of the first one, we would get 1 over x cubed plus x, because that's the derivative of ln. But then we would have to multiply, because of chain rule, by the derivative of x cubed plus x, so 3x squared plus 1, and that's how it would end up in the numerator. Now, just for the sake of the fact that some of you might not be able to make that jump, it might not be as intuitive. Some of you might, some of you might not. So I will go through the substitution steps as well, just to make sure just to show another way in which you can get set answers. So with substitution, let me just erase these now. With substitution, we're going to make the denominator our u. So we're going to make u equal to x cubed plus x. Actually, I'm going to write this over here. So u is equal to x cubed plus x. So that means the derivative of this, as we talked about before, is just 3x squared plus 1. If we solve this for dx, we get du over 3x squared plus 1 is equal to dx. So now we make our substitutions, right? So the integral of 3x squared plus 1. So the bottom, remember, at this point now becomes u. Okay, that becomes u because that's what it's equal to. And then the dx now becomes du over 3x squared plus 1. So at this point, hopefully you can see that there will be some cancellation. The 3x squared plus 1 cancels out. And now all we're left with is the integral of du over u, which we can easily rewrite as the integral of 1 over u du. And once again, the antiderivative of 1 over u is the natural log of u plus c, since we're not doing an interval this time. So we just plug in u back in, so the natural log of the absolute value of x cubed plus x plus c, which was what we originally thought the answer was. Now, if we do the same thing for b, so we set u equal to tangent of x. That means the derivative is secant squared of x. If we solve for dx, we get du over secant squared of x is equal to dx. If we make the substitutions, we get the integral secant squared of x over u now, right? Because that is what tangent of x is equal to. Tangent of x is equal to u. And now dx is equal to du over secant squared of x. So that dx is replaced with a du over secant squared of x. Just like the other problem, the secant squareds of x's cancel out. And now we are left with the integral of du over u, which is just the same thing as the integral of 1 over u times du. Antiderivative time, 1 over u is the natural log of the absolute value of u plus c. So our final answer, just as we predicted, is the natural log of the absolute value of tangent of x plus c. So, if you can do this intuitively, that's great. It's quick. It's efficient. If not, it's okay. You can still use the substitution, and you will get the same answer. All right, so now let's move on to ones that are actually going to be similar to the previous one, though we will have to do a little bit of trickery here, or a little bit of manipulation to get the answer that we want. So the first one's C. So if we try to use the same strategy, so we got x squared plus 2x. Well, the derivative of that is 2x plus 2. Well, that's not x plus 1, but if you notice, it's double x plus 1. So I could just multiply this by 1/2, and I get that x plus 1. So let's see. Could the answer just be the natural log of the absolute value, x squared plus 2x, with a 1/2 in front? Well, if you would do the derivative of this, so if you were to do the derivative of this, you could pause the video, for example. If you were to do the derivative of this, you would get 1 over x squared plus 2x. Right? So that 1/2 would still be there. And then you would have to multiply, because of chain rule, by the derivative of the inside. We just said that the derivative of the inside is 2x plus 2. So you would get 2x plus 2 in the numerator. Now, since we're multiplying by 1/2, though, that 2x plus 2 in the numerator would reduce to x plus 1. So it looks like our answer is correct. And we could do the same thing with D, right? We know the answer, or the derivative of 3x plus 2 is just a simple 3. Now, this is actually similar to a problem we did on the front of the handout, where we want a 1 in the numerator, not a 3. So we could just multiply by 1/3, and that would give us our 1. So does that mean our answer is the natural log of the absolute value of 3x plus 2 with a 1/3 in front? You would see that it is exactly that. And once again, how do you check it? Take the derivative. The derivative of ln, in this case, would be 1 over 3x plus 2. Multiply by 3, because that's the derivative of the inside. And then the fact that we already have a 1/3 would cancel out that 3. So you would end up with, indeed, 1 over 3x plus 2. So once again, intuitively, that's how you would do it. Now, let's use the substitution to see if we get the same answer. Let's use a substitution to see if we get the same answer. So if we use a substitution, we're once again going to make u equal to the denominator. So u is equal to x squared plus 2x. So the derivative of u is equal to 2x plus 2. Let's solve for dx. So let's see, we get du over 2x plus 2 is equal to dx. Let's make the substitution. So now we got the integral x plus 1 over, remember the x squared plus 2x is now a u, and then times the dx is now a du over 2x plus 2. So at this point, if we simplify, hopefully you can see that since both of these have a 2, we could factor out a 2. So we can rewrite this as the integral of x plus 1 over u times du over 2 times x plus 1. And now the cancellation of the x plus 1s becomes a little bit more apparent. And now we can write this, very similar to how we did the other problems, as 1 over 2 times 1 over u du. We do our antiderivative, natural log of the absolute value of u, except this time we have 1/2, plus c. So our final answer is 1/2 natural log of the absolute value of x squared plus 2x plus c. Exactly what we thought it would be. If we try the same thing with D, this one should be a little bit shorter. So u is equal to 3x plus 2. The derivative gives us 3. Solve for dx. Du over 3 is equal to dx. Make the substitution. The integral of 1 over, remember 3x plus 2 is now a u, times the dx is now a du over 3. Nothing cancels out this time. We just have some constants involved. So we have the integral 1/3 times 1 over u du antiderivative, natural log of the absolute value of u, 1/3 is in front, plus c. So our final answer is 1/3 natural log of the absolute value of 3x plus 2 plus c, which is exactly what we thought it would be. All right? So once again, intuition can be helpful. You're not always going to be able to do it. Some of you, I've noticed, are good at it. For some, it looks like you have to do the step-by-step substitution, which is okay, as long as we get that correct answer. All right, I think we have 2 more examples here. So this is a change of variable one. This is the one where, if you notice, we can set u equal to x plus 1, but if we take the derivative, that just gives us a 1. But we have this 2x on top of our equation, and we got to get rid of that somehow. So if you recall, the way we did this is we still set u is equal to x plus 1, and we still set du over dx is equal to 1. But this time, we solve for x in the first equation. So u is equal to x plus 1 is the same thing as saying that u minus 1 is equal to x. Well, we want 2x. Well, I just multiply both sides by 2. You get 2u minus 2 is equal to 2x. So now not only do we have the substitution for x plus 1, we have the substitution for 2x, and we have a substitution here, if we quickly solve for dx here, we have a substitution for dx. So we can rewrite this as the integral. So now 2x is equal to 2u minus 2 over, remember, u is now x plus 1. We just got u squared, and now du is just dx now. Now, so let me just rewrite it here so it looks a little bit more clear what we have. So we have the integral of 2u minus 2 over u squared du. Well, you might be wondering, well, how is this easier for us? Well, remember, you can separate this into 2 fractions, people. So 2u over u squared minus 2 over u squared du. Now, the 2u and the u squared, there is some cancellation here, so 1u cancels out. So now we have the integral of 2 over u minus, remember when your exponent is in the denominator, we can rewrite it as a negative exponent, du. And now I can rewrite 2 over u as 2u to the negative first. Now we can finally do our antiderivative. Or actually, I'm not going to rewrite that, only because it's a little bit more easier for us what we have to do. So now the first one, the antiderivative of 2 over u, remember, is just the natural log. So the natural log of the absolute value of u, 2 in front there. And then minus, for this next one, we do have to do the reverse power rule. So we have to add 1 to the exponent. So it becomes 2u to the negative first, and then divide by that new exponent. So divide by negative 1. So plus c. So I'm going to rewrite this as 2 ln as the absolute value of u. We have, let's see, we have a negative divided by a negative, so that becomes positive. So plus 2u to the negative first plus c. Now at this point, I'm just going to substitute back in u. So 2 natural log of the absolute value of x plus 1 plus 2 over x plus 1. And remember, I can put x plus 1 in the denominator at this point because it was to the negative first, plus c. So that would be our final answer for that one. A little bit trickier, mainly because we have to do this change of variable method. All right, this last one is tricky only because it's not obvious what you have to do. Okay, it's not obvious what you have to do. The trick here is recognizing, all right, I have an x squared plus 1 here on the bottom. I have an x squared plus x plus 1. Darn it, I'm so close. If I just could do something with this x, I could just cancel each other out. Well, you kind of can. You can rewrite this. You can separate this a little bit. You can separate this as the integral of x squared plus 1 over x squared plus 1 plus x over x squared plus 1. So I literally just separated them. It's kind of similar to what we did in the previous problem. I just separated them into two fractions, one fraction with the x squared and the plus 1, and the other fraction with just with the x. Well, this is very convenient for us because now this just cancels out. That's just 1. So now what we have here is the integral of 1 plus x over x squared plus 1 dx. Now, for the purposes of this exercise, since we've done an antiderivative very similar to x over x squared plus 1, I'm going to leave that as an exercise for you guys using substitution. The answer that you should get, so if we do the antiderivative of this, you'll get x, and then you'll get plus, make sure I get it right here, 1/2 natural log of the absolute value of x squared plus 1 plus c. Okay? So once again, the antiderivative of 1 becomes x, and the antiderivative of x over x squared plus 1 becomes that. That might have even been one of the problems that we did. Or no, I'm trying to remember. Yeah, it was the example 2 problems. You already did the antiderivative of that one. You can do it again just to make sure you remember how to do it by substitution. But otherwise, that would be your answer. That would be the trick for this problem. I know it's not very obvious that's what you would have to do. So it comes with, obviously, it comes with more experience figuring out that those are the kinds of things you can, you're allowed to do. I mean, one trick that I think going forward can be useful is just knowing that you can separate, something like this into multiple fractions. Always remember that is an option. Now, whether that'll always be helpful is another thing. As we've seen in this example and in the previous example, separating it into multiple fractions can be helpful, but not always. Please let me know if you have any questions, if anything else seems unclear. Otherwise, I hope this was a good conclusion to the lesson. Tomorrow we will be moving on to a new lesson. It'll actually be the same topic, just some different examples tomorrow, still with ln. But if you do have any questions, you can always either post a comment on here or ask them in class. Otherwise, hope you guys enjoy the rest of your evening, and I will see you tomorrow. Bye-bye.